Next slide. And turn on my projector. And pick a bone with you two, or actually I wish all three were here. You let me get away with something last time.
When I left, when I got to the gym, I was like, man, I'm here awfully early.
I know. I got down to my office. I said, what? This is time? And I think what it is, we got started early, and then, and Corey, I thought, stayed longer than he had planned to, and then he started getting ready, and we usually leave it near 5 till for the previous class, and it got almost 5 till. I said, oh, it's time to go, because it's the same 3 people, and same 3. And I just thought, oh, I ran over, and ended it, got down to my office, and went, wait a minute, I'm not supposed to be here this early. So, sorry about that. I cheated you out of some of your tuition dollars there. $1,380 at least. So, but no refund. Okay, this time it goes that way. All right. I'll try not to do it this time. Let's see, we're supposed to end this thing this time at 3:15 now. Is that right? No. No way.
Usually 3:45.
3:45, so now it's 3:30. Okay, got it. Okay. So I really cheated y'all last time. Okay, and we could have gotten considerably done on the next. I don't know. I don't know where my brain was, but it wasn't where it needed to be. Anyway, 2.6. Any questions on anything we've done so far? All right. 2.6 is a numerical method, okay? And I guess it's, okay, no one uses this anymore, and that's why I'm a little surprised I say no one uses it. I don't know of anyone that does, but it at least gives you a concept of how these numerical methods can work, and you almost have to have computer packages to do the more complicated ones. So I guess it's okay just to do this one. But if you recall, we've done some things like this before. A differential equation can be a source of information. Okay? We started this chapter 2, by observing we could gather qualitative information from a first-order differential equation about its solutions even before we started to solve the equation, okay? And then 2 through 5, we actually solved them analytically, which to me is the fun part, okay? That is, we developed some procedures for obtaining explicit or implicit solutions. But a differential equation can possess a solution, and yet it may not be possible to obtain it analytically. So to round out our picture of different types of analysis of differential equations, we conclude this chapter by a method by which we can solve a differential equation numerically. Okay? And that means the differential equation used as a foundation will construct an algorithm for approximating the unknown solution. And approximating is the key word there. Okay? We're not going to get an exact solution. But guess what? In real life, a lot of times equations are so complicated and so convoluted that to obtain a real, an actual solution to them is, you're going to have to use numerical integration, numerical solutions. So they're going to introduce you to one here, which isn't a particularly great one. It was developed a long time ago by Leonard Euler, so it's called Euler's method. But it does give you a decent approximation, okay? So what we're going to be doing is using the tangent line. Now, a little bit of this sort of reminds you of Newton's method for finding the zeros of a function. That uses the tangent line. But boy, that zeroes in on it and gets you there in a big hurry. This one, the more you do, the further off you get. So this isn't quite like Newton's method for finding it. They're just two completely different problems. So let's assume that we have a first order initial value problem. That y, let me get my pen set up. That y prime is equal to some f of x. xy, okay? And that y at x0 is equal to some value y0. Okay. And we're going to assume it has a solution, okay? That it's not something that's going to fly out, you know, and start going to infinity and you can't possibly get there, approach some singularity and can't possibly get a solution. We'll assume it does have a solution, okay? Now, one way of approaching the solution is to use tangent lines. And really that first thing is a tangent line, okay? Y prime is equal to f of xy. You can, and we have an initial point, x0, y0, and you can plug that in and know what your tangent at that point will be. If you know what that function is, you can plug in the x0, y0, and you know which way it's heading from there. Because y prime would be equal to f of x0, y0, if you knew what that f was. Okay. Now, let's let y of x equal, that would be the solution. This is the unknown solution for this problem. Y prime is equal to 0.1 times the square root of y plus 0.4 x squared. Okay. And we'll say we have an initial value of y of 2 is equal to 4. Okay. Now, let's just take a look at this. Certainly that's nonlinear, because you have a square root of y in there. Not linear. Okay? Not separable. Okay? Not in any sensible way. Any of the other techniques we have can't solve it. I mean, it looks so simple, but it's just not solved. Okay? Not with any of the methods we have so far. So, what we're going to do here, this nonlinear cannot be solved any way of the methods considered in 2, 4, or 5. Why did they leave out 3? That was 3 anyway. Oh, it's nonlinear, so we already excluded that. Nevertheless, we can find an approximate numerical values for the unknown y of x. Okay? So let's say we want to know y at 2.5. We know y at 2, but we don't know, we want to know what it'll be at 2.5. Okay? Now, this is what they're calling the f of xy. Okay? And that's also what, and that's your first derivative of your function that we're looking for. Okay? Now, so let's figure out what at 2, 4, where we're heading. Okay? So your y prime, which is equal to f of xy, which I'm going to go and write down. Two, 4. We know the value there. Okay, so this is going to be 0.1 times the square. I don't need parentheses there. times the square root of y, which is 4, plus 0.4 times 2 squared. Okay? So our y prime there is going to be 0.1 times 2 plus 0.4 times 4, which is equal to 0.2 plus 1.6 equal 1.8. Right? There's your first derivative of, there's where the function's going at the 0.24. It's going to have a slope of 1.8. It's going to be going up 1.8, or up 18 units for every 10 units that goes across, or 1.8 units for every 1 point it goes across. So however you want to say that. 9 up for every 5 across. That would be right, wouldn't it? No. Yeah, okay. Something like that. Okay. So, yeah, 9 to 5. Now, let's say that that's going in that direction, okay? We know it is, 1.5. So let's make a linear approximation of where this is heading, okay? We know the slope is 1.8, okay? So we're going to have some L of x is equal to 1.8x plus some value, let's call it b maybe, okay? Now, because the 0.24 has got to be on that, see what happens if we do 4 is equal to 1.8 times 2 plus b. What does that give us? 4 is equal to 3.6 plus b. So that would imply that b is equal to 0.4. Right? Okay? So our first approximation of the L of x is equal to 1.8x plus 0.4. That's going to head us in the right direction and inch us forward there. Okay. Now, what we'll do at this point, that's what we call the linearization of y of x at x equal 2. Because we plugged in x equal 2, we knew it was heading toward 4, that gave us a b of 0.4. Okay. And we can use that to approximate the value in a very small neighborhood around x equal 2. Okay. Now, let's say that y1 is, our next approximate value is going to be L of x1. Okay? So let's say that the next point we choose is 2.1. So y1 would be L of 2.1, which would be 1.8 times 2.1 plus 4. Okay? So this time, y'all use a calculator and help me out here. 1.8, that's 0.4. Okay, sorry about that. 1.8 times 2.1 plus 0.4. You got it? 1.8 times 2.1 plus 0.4. 4.18. Okay? That's our next approximation. The first was 4, so now we're going to be at 4.18. Okay. Now, that would be 2.1. Then we could keep going from there and try to approximate where we're going to be at 2.5. Now here's how Euler's method has us do it. We've got that down. Let's do a little bit more for Euler's method here. Okay. Now what we did there, just to get you an idea, your L of x was your previous y0 plus, okay. Let me just write it down. Okay. Your linearization of x, linear approximation of x, is going to be your y0, the y value you started with, plus this f of x0, y0, that's going to be your slope, times x minus x0. Okay, now I don't know if this rings a bell with you, but that's awful close to being what we would call our point slope formula. Okay? Okay, it's not a straight line, but if you were using it as a straight line, this would be your y value. Y minus y0 is equal to the slope, which is that's what the slope is, times x minus x0. Okay, so that's what we're basing this on. This is going to give us a new y1. Okay, and then we'll use that y1, put it here, and then do an x1, and put the y1 here, and then x minus x0, and keep going from there. So, or x minus x1. Okay, for some new value. Sorry, I worked on the farm all weekend and overused my leg, and my knee is just stiff today. Achy would be the best word for it. The graph of that linearization is a straight line tangent to the graph at y equal y of x at the point x0, y0. And we'll let h be a positive increment of x-axis. And for the first, what we did up there, we let the h be 0.1. Okay? So I think what we'll do is probably use that. So what your next point would be, L of x1, the next value you would have for your x1, and let's say it's 2.1 for this case, where h is 0.1. That would be, sorry, okay, your y0 plus f of x0, y0, okay, times your x0 plus h minus x0. Okay, now that seems a little bizarre, but what we're doing is letting x1 be x0 plus h. So, or x be x0 plus h. So you put that in there, and the x0 is going to go out, or add a 0, and you just have an h there. Okay? So that then would be y1, that's what we're going to call that L of x1, is equal to y0 plus f of x0, y0 times h. Okay? Well, I'm sorry. They're doing the next one. That would be x1, y1. Okay. In other words, I think they've got it backwards. I think that has to be x0, y0. Because otherwise, you'd be using y1 to calculate y1, and you wouldn't know what y1 was. Okay? So I think they've got that wrong. I think that has to be 0. So I think I was right the first time. Now they put the h in front, which is fine. Where y1 is equal L of x1, and the point x1, y1 on the tangent line, blah, 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 blah. Okay. So everything depends on the increment h, how big a step you're going to take at a time, and how we go with that. Okay. So let's just write down our y at x2 would then be y1 that we just calculated plus h times, h times f of x1, y1. So I think that had to be x0, y0 up there. Okay. I think they just put it wrong here. Okay. And that's how we're going to continue. Okay. So basically your formula is y sub m plus 1 is equal to y sub n plus h times f of x sub m, y sub n. X sub n, y sub n. Okay, they don't put a parentheses in front, so that's where it's getting ugly there. And then, yeah. So there's your regression, the formula. And that's Euler's method. Okay? Each one is a tangent line based on the previous. So let's go back to the one we started with. Of y prime is equal to 0.1 square root of y plus 0.4 x squared. Given the initial condition, y of 2 is equal to 4. Okay. And we're going to try to get to y of 2.5, and we're going to do that first using h of equal to 0.1, and then we'll do it with h is equal to 0.5, not 0.05. Okay, and I'm not going to do all those, I'll promise you. Okay, all right. So let's do just again, this is your f of xy is equal to that thing. Okay. So, Euler's method says y of n plus 1 is equal to y of n, y sub n, plus h times f of x n y n. I keep putting a parentheses there that they don't do, and that just makes it okay. All Now, and for us, for this problem, that will be y sub n plus h times, and this is our f, 0.1 times the square root of y plus 0.4 x squared. Okay. Now, let's do y sub 1. H is 0.1 to begin with. One thing sort of bugs me about this, and I'll let you know that really soon. Okay? Y sub 1 will be y sub 0, which happens to be 4, right? Plus 0.1, that's the one we're going to do first, 0.1 times, that's the decimal point. That's your h. Now I'm going to put the parentheses, 0.1. Why in the world couldn't they have given us a problem that wasn't the same thing, first number, times the square root of 4, which is 2. Well, I'll go on and write it this way this time. Plus 0.4 times 2 squared. Okay, and we've already done this. So this will be 4 plus 0.1 times 0.2, because 0.1 times 2 is 0.2, plus 0.4 times 4 is 1.6, okay? And this was 4.18, wasn't it? Okay, was that right? I'm just doing it from memory now. Okay, because that'd be 1.8 times would be 0.18. Got it. Okay. So our y2 is going to be 4.18 plus 0.1 times 0.1 times the square root of 4.18 plus 0.4 times 2.1, because that's your next increment up, your x plus h squared. Okay? So some of you with calculators, sock it to it. Just be careful about hitting your parentheses closed. 4.18 plus 0.1 times open parentheses 0.1 times square root of 4.18. Make sure you close that, because the square root will open 1, you close it, plus 0.4 times 2.1 squared, close that, equal. And hopefully you're punching your calculator and getting your parentheses correctly. What do you get? Anyone got a calculator?
Oh,
You're trying to do it on the computer one?
yeah.
I didn't. Oh well. Only calculator I have here is a cheapie. I could have. Say again? No. It's going to be 4 point something. So let's see if we got our parentheses right. 4.18 plus 0.1 times. And open your parentheses there. 0.1 times the square root of 4.18. You have to close that square root. Okay? Plus 0.4 times 2.1 squared. You can do that without parentheses. Close parentheses. That's pretty close. 4 well, not 04, 4.4 is close. Yeah. What they get in the book is 4.3768. Now they carry it to 4 decimal places. The other one was 4.18 exactly. This is a round off. You get it yet on your calculator?
I can hit the right button.
You're convinced it'll be right, huh?
Well, I got 4.244. Let's type something wrong.
Yeah. Well, that's,
on the other one, I would just plug in this formula
mm-hmm.
on the other calculator. It just set the variable. You can set the variables for whatever you want.
Right.
And just keep.
Right. But it's not working now or something?
Well, it's got to load and do all this stuff.
Oh, I see. Okay.
It takes forever.
Okay.
Because I never turn it on.
All right.
This is
All right. And just to continue, that would be your Y2, so your Y3 would be 4.3768 plus 0.1, because that's your increment, and this 0.1 was part of your problem, times the square root of the Y, which is 4.3768, plus 0.4 times 2.2, because you step that up a notch, squared, and then you see what that one is. .3768 plus 0.1 times open parentheses 0.1 times square root of 4.3768, close that, plus 0.4 times 2.2 squared, close parentheses. They got 4.5914. I don't know how. 4.5914. So it sounds really close. Okay. Now, what they may be doing, and if they're doing it, I'm all in favor. Okay. And here's what I would be doing if I had one of the calculators. Okay. This one came out exact. Okay. So it'd be 4.18 plus 0.1 times open parentheses, 0.1 times square root of 4.18, that was exact, plus 0.4 times 2.1 squared, and hit equal. Now, they wrote down 4.3768, but your screen carries it on out as many digits as you got. So I would take that number that's on your screen, save it to some value, to some place in your computer, and then start with that whole number. They're approximating it by this, but start with the whole number plus, and when I say whole number, all those digits, okay, plus 0.1 times 0.1 times the square root of, recall that whole thing, plus 0.4 times 2.2, because that's all we're doing on that squared, and then do an equal, and then you get another whole set. They're recording the first 4 digits. So that's what may be where the error is. They're probably hauling all those digits with this rounding to this every time, because it sounded like you were awfully close. Okay, and that's what my guess is. This is a round off, but what I would do is carry that, save that in that same spot again, put that number here, that all those digits, plus this, and then put all those digits here, and then plus the other. And keep going, stepping this up every time you step that up. Okay? And they would ultimately get to blah, 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 y sub 5 is equal to 5.0768. Okay. That's your estimate. Okay. Euler's method with a step size of 0.1. Okay. Now, let's go to a step size of 0.05. Now, I don't have room to do it here, so I'm going to start over. And that would be yes, ma'am. Okay. Sorry about that. Now, let's start over and with I'll write the whole thing down again. Y prime is equal to 0.1 times the square root of y plus 0.4 times x squared. Right? Yeah. And y of 2, yuck, I keep putting a comma after that, and there's no reason to. Comma is equal to 4. I guess I'm thinking at the point 2 comma 4. Okay. But that's not what I'm writing. That's what, okay. So, here your y1 is going to be y0, which is 4, plus 0.05, that's our new increment, okay, times, I'm going to put a bracket there to make it more obvious here, 0.1, that's part of your problem, okay, times the square root of 4, which is 2, but I'm going to write it as square root of 4, plus 0.4 times 2 squared, which we know what that is, and that is equal to, okay, we can do this one by hand, 4 plus 0.5, 0.05, no wonder I make mistakes, times 0.1 times 2 plus, this is all the same, 0.4 times 4, and that would be 4 plus 0.05, and this part came out exactly the same. 0.2 plus 1 point, that's 1.8. So this is going to be 4 plus, now someone do that for me quickly, 0.05 times 1.8. 0.05 times 1.8. 0.09. Okay, so that would be 4.09. Last time it was 4.18. But we've only gone half as far. We're at 4.05 now. Okay, I mean, okay, 2 point, okay. So our y2 is going to equal 4.09, and by the way, that's what they got there too. 4.09 plus 0.05 times 0.1 times square root of 4.09 plus 0.4 times 2.05 squared. Okay? See what that gives you. 4.09 plus 0.5 times 0.1 times, be sure you do an open parentheses after that 4.05. 0.1 times square root of 4.09. Be sure you close your parentheses after that square root. plus 0.4 times 2.05 squared. Close your outer parentheses and hit equal. What you get. Have you got it yet? Now, I want to point something out for you now. This y sub 2 here is 2 increments of this past the 4. Well, 2 increments of this is 4.1 now. Okay? I mean 2.1. So basically, this y2 compares to y1 before when we did an increment of 0.1. This is 2 increments of 0.05, which makes an increment of 0.1. Last time we were 4.18, now we're 4.1842. So this is inching up a little bit closer to what reality is. Now, they showed you the graph of this in your text, and you saw we were underneath the curve, okay? And so, therefore, every bit you went, you're still going to be beneath. But with doing a smaller increment, you're getting closer to where that blue curve is, okay? And the 4.1842 is closer than 4.18 was, but it's still not up there. Did you ever get it? No. Okay, sorry.
I'm still trying to figure out how to do these things.
Do you want me to?
I think I just got it.
Oh, you did? Okay.
Now I got to plug in the different numbers. So
Doing the other one.
The other one.
Okay.
Give me a weird error.
Yeah. And this is 4.1842 plus 0.05 times 0.1 times the square root of 4.1842 plus 0.4 times 2.1, because you step that up 0.05 squared. Close that parentheses and see what you get. The book got 4.2826. Now, I'm not doing it, so I can't swear that's true, but I assume it is, because that's what they got. And then you would take that and do the next one, y sub 4, which is 2826 plus 0.05 times 0.1 times the square root of 4.2826 plus 0.4 times 2.15, you step that up by 0.05 squared, close parentheses, and equal. Now this one is at the point 2.2, okay? Because you stepped it one up from point 2.15, and in the book, does anyone get that yet? 4.3814. Now that should be equivalent to your y sub 2 before, when it was 2.20, and that was 4.3768. We're at 4.3814. So again, we're leading it just a little bit, leading the previous one. Still are up to where the actual is, but you see we're getting a little bit closer. And you could do this, of course, the downside of this, you got twice as many steps to take, okay? The upside, every time you decrease your increment, you get closer, but that increases the number of steps you take. So therefore, this is something you do on a computer, okay? You program it to do this. And this would not be a miserable thing to program, except maybe on your computer, okay, on your calculator, okay, and you just let it go as many times as it takes. This time, last time it would have gotten there in 5 steps. This time it will take 10 steps to get there, but you'll be closer to where the answer was, okay. Now,
for the sake of argument, when you're doing increments, why do you want necessarily decrease them way down? Why don't you want to do that?
well,
Accuracy?
yeah, to get more accuracy in what you're approximating, because I don't know if similar to the concept of round-off error, okay, if you're a little off this time, but you use that result the next time, it's going to be a little further off, and then a little further. You're getting closer, but you're not getting as much. So this time you're closer the first time, and every time is going to be a little closer than the other. You're still, now what did it buy you? Here they're y sub 10, I think it would be called. That would get them to 2.50. That's what you hope it's, I mean, that's going to be when x is equal to 2.50. So I shouldn't do that. This y sub 10, that's an ugly 10, but that y sub 10, they came out to be 5.0997. And before, their y sub 5, when they did the 0.1 increment, and that also was 2.5, x equal 2.5, they came out 5.0768. This is certainly closer. We don't know what the exact answer is because it's not one we can solve, but we do know that was closer because of our curve. The tangent line started us off below the thing, and so it's never going to get any closer. I mean, it's never going to cross it, whereas Newton's method would zigzag along and keep getting closer and closer. This one, if it starts below, it almost is always going to stay below, okay? Unless your curve does a real sharp turn somewhere up there before you get to it, then you may look up. But this gets closer. But notice it's not a lot. I mean, that's 0.02, maybe a little over 0.02. And so it's not a bad approximation, okay? Now, that one we didn't have an exact solution, so we couldn't compare. So they're suggesting, why don't we do another one that we already know what the solution is and see how close we get, okay? All right, to erase? So let's go back to one we've done before. Consider this initial value problem. Y prime is equal to 0.2 times xy, where y of 1 is equal to 1. Okay? So we're going to use Euler's method to obtain an approximation of that using first h is equal to 0.1 and then h is equal to 0.05. Okay. So that's this is our f of xy. Okay. So our formula again is y of n plus 1 is equal to y sub n plus h times f of y sub n, x sub n, y sub n. Okay. So this time it'll be y sub 1 is equal to y sub 0, which is 1, plus h, which is 0.1, times 0.2 times 1 times 1. Because you're starting x equal 1, y is equal to 1. So that's formula a lot simpler this time. So let's just do it here. That would be 1 plus 0.02. So that would be 1.02. And that's what they got. So your y2 will be 1.02 plus 0.1 times 0.2 times 1.1, that's your x, times 1.02, that's your y1. Okay, now this should be a lot easier to do on the calculator. 1.02 plus 0.1 times, and you can just do a single parentheses there, 0.2 times 1.1 times 1.02 equal. I mean, you don't need a parenthesis, just times. 1.02 plus 0.1 times 0.2 times 1.1 times 1.02 equal. What you get?
1.0211.
Okay. The 212.
Yeah, I don't know how you round that up.
What did you get?
1.021122.
1122. Okay, I don't see it either. Huh?
That's close to my first.
Yeah, okay. All right. And y sub 3 would be 1.02. I'm going to use what they got, 12, plus 0.1 times 0.2 times 1.2 times 1.0212. And what did that equal? Zero 457. They got 1.45. Okay. Yeah, this is something that doesn't make any sense to me. Oh, I'm sorry. Sorry. Okay. The first was 1.02. The next one, they got 1.0424. You didn't get that. They didn't get 1.0212. You see, they're going down the column there. Next to that is the actual value, because we can do this one. We know how to do this one. Okay. So, I'm sorry, I was not following the book, so let me, yeah, because I thought that was a huge jump there. Okay. So this next one should be 1.0424. And the next one should be 1.0675. Now, I don't have a calculator up here to do it, so I'm just assuming what they're doing is fairly close to correct. Yeah, it looks like you'd be going up by something like 0.02 every time, because 0.1 times 0.02 times 0.2 would be 0.02, and then you're multiplying that by something slightly bigger than 1 twice, and so you'd have to be going up by something a little bit more than 0.02 every time, and 0.02 to the first one. Oh, don't forget to go back and change this too. I'm sorry. That's 1.0424, and this is 1.0424. So that gives you a 1.06 something another. So your y sub 4 would be 1.0675 plus 0.1 times 0.2 times 1.3 times 1.0675. Yeah, we have done this problem before, not with the approximation. Oh, you have? Okay, maybe you did. Yeah, I wouldn't be surprised if you didn't do some iterative processes like this. Yeah, and that's going to go up, I'm sure, more than 0.02 this time. That jumps up to 1.09. 52 is what they said. Okay, and so you keep going, and finally their y sub 5, they say, is going to be 1.1259. Okay. They're going to do it with the 0.05s. I wish I had room to write it on the same page, but I write too big and not going to get there. When they do that, and get to 1.5, they're 1.1295. So it's just slightly bigger, but the actual value is even a little bit bigger, 1.1331. So you see your absolute error is very small, and your relative error is very small. In fact, your relative error on the 0.05 increment is half what the relative error is on your on the 0.1. And they talk about that some too. So it's just giving you an idea of how good or not so good Euler's method is. Okay. Now they give a little caveat there at the middle of page 79. Euler's method is just one of many different ways in which a solution of a differential equation can be approximated. Although attractive for its simplicity, Euler's method is seldom used in serious calculations. So why did they ever do this? Okay, it was introduced here simply to give you a first taste of numerical methods. We'll go into greater detail in discussing numerical methods that give significantly greater accuracy, notably the fourth order Runge-Kutta method, referred to as RK4 in chapter 9. I doubt if we're going to get there. Okay.
Well, it seems like it's on the computer anyways.
Yeah.
So what's...
We are. So anyway, you get this, a computer program written to either implement a numerical method or to render a visual representation is referred to as a numerical solver, for what that's worth. Okay? And then, whereas others generate hard numerical data as corresponding approximate or numerical solution curves, and they just go into using a numerical solver and then showing you some of the not very helpful numerical solution curves you could get if you happen to choose an increment that happens to send you crazy. And that's this one. But just for reference here, your exact solution to this one we're just working on is the blue curve here. We haven't learned how to do RK4. But RK4 obviously attaches itself to the actual function at 1, 2, 3, and 4. So their in-betweens are going to overshoot slightly because the curve is curving up. Euler's method, because of the tangent, is undershooting. And you see it gets way off here. Obviously on the points you're exactly on, but in between you're really close with RK4. With Euler, the further out you go, the further off you get. But then here's a not very helpful numerical curve that just goes kind of crazy there. But to me, that's not worth spending a whole lot of time on. Now, that finishes 2.6. You can do problem number 1, if you wish. Its answer should be in the back at ANS-2. You can do number 3 if you can find its answer back there. And then any of the odds 5 through 9. And if you can find 11 back there, you can certainly do that. And then there's only one discussion problem. I doubt if it's back there, but if there is, you can look at it. Now, that ends chapter 2. And if you need more practice, any of the odds 1 through 11, those answers are in the back. 13's in the back, 15's in the back, 17's in the back, 19 through 25 are in the back, 27 or 29 are in the back, 31's in the back, 33's in the back, 35, I'd say any of the odds 35 to 39. You choose. That finishes chapter 2. I think I've gotten maybe test 1 in. I'm ready to do a test 2. I say ready, that's figuratively speaking. I don't have test 2 run off yet. I have test 2 made out, but I don't know if I have enough copies. I've got to find it first. There's test 2. There's test 2. There's test 2. Okay. I've got 1 copy already, and I need to run 2 more. You want to wait till the end of the class and I run those, or do it now? Huh?
I don't care. We only have 6 minutes anyways.
How much?
6.
Okay. Okay. 6 minutes left, is that what you said?
Yes, sir.
Okay. Well, I didn't know. Last time I ended too soon. This time I thought we were just gotten going. Okay. But those take a long time. We're not doing chapter 3. I don't believe anything in your course description mentioned modeling. Though it's fun stuff, but we just don't have time for all this. Let's move on to chapter 4, which is higher order differential equations, which is a very long chapter. So we're not going to do every section in here, but we're going to do a certain number of sections and get as far as we can. And if we get far enough, we might go beyond this, but my guess previously we've basically But we're actually making better progress this time than we have other times I've taught this. So we might actually get out of chapter 4. But chapter 4 is so stinking long, quite often we don't quite get through with it by the end of the term. I think this time we will. But just taking a look at it, we'll do 4.1, which is one of those blah, 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 esoteric, feel good about it thing. And then we'll do 4.2, which is a little more practical. But then we start the real stuff with 4.3. And when we get that done, 4.4. We will not do 4.5. Those are two different approaches to undetermined coefficients. I found that students tend to respond better to superposition approach than the annihilator approach. They really are doing almost the same thing, but it takes less time to, at least for the book and me, to cover 4.4. So we went with that. Then we'll move on to variation of parameters, and then we'll pick and choose what we're going to do after that. We may stop after variation of parameters and move on to the next chapter, which I think is not chapter 5, because I think chapter 4 is really long. Chapter 5 is modeling with higher order differential equations, since we aren't required to model. Chapter 6 is series solutions of linear equations. I don't think that was in our course description either. And chapter 7 is Laplace transform. So if we do finish chapter 4, we'll move on to chapter 7. But let me, meanwhile, do either one of you need to head out sooner than the other? Because I got one copy. I can give one of you right now. Goodness, I'm just kidding. Huh? And I'll go make 2 copies, one for Bill and one for Corey. So that'll be it for today if we've only got just a couple minutes left. Wow, today flew by. I should keep you extra for last time, but no, I guess I won't. All right. So let me go to the front.
I just can't do it another one.
Yeah, I just got a copy on mine down from the computer.
I still didn't get that damn thing.
And finish, I think 2 problems on the Cal 3 test.
Just do the best I can. Yeah, look at my age. Give it a break.
You should give you bonus points for every birthday you have. Or have had.
Well, the business professor was asking me, he said, how are you doing? Ain't nothing. So it's good. Only reason he said that is looking at me and saying, I'm younger than he is. Oh, I got a cold Saturday.
Yeah, dude.
I'll be real quick, about 4 o'clock. Because the temperature had been up, I guess, about in the, at least the 70s. About 4 o'clock. Oh, man. Try to make the day of it.
I got a copy of them down, because I don't think I can, well, I don't know, I might be able to print them out from my computer, where I work them out, but I'll probably just clean it up and write it down.
I lost the whole week. The computer went down on me again. My son was telling me, he said, look, well, did you go to the place and do that? I said, yeah, I went to the library to print out something. He said, all that happens when you went home to the library. I said, well, text you. He said, okay, what you did was you convert your computer over to Gmail or whatever, and he got you to print out what he wanted, but he forgot to do so. We opened up certain bars, he
I just realized I put my thing on hold, but I would have started back right now. Sorry about the dead time there, but let me just briefly go over what you're expected to do here. Question 1 is not supposed to be really, really hard. It's a lot more straightforward than probably what you would guess when you first read it. So don't make it any harder than it is. I'll put it that way. Question number 2 is dealing with a absolute value type thing. So I don't think that one's particularly hard either, and again, don't make it any harder than it needs to be. Number 3 is talking about one of those autonomous linear first order single critical point, okay? And it just says, give an example where with a single critical point, and then give one with a nonlinear first order differential equation with a single critical point. Again, they're not that hard to do. Don't make it into something that is super hard. Now, number 4 is the bulk of the test. Okay? What you're to do is just classify each differential equation as one of the following: separable, exact, linear, homogeneous or homogeneous, or Bernoulli. One or more of those 5. And some of these will be multiples, okay, as indicated there by having multiple blanks, okay? So that's all you're doing is classifying, do not solve. Okay, that would take forever if you had to solve all these things. Well, it wouldn't, but it would take a while. But then in problems 5 and 6, those you solve. I knew you wanted some more logs there, so there's some logs. Yay, okay.
Oh, man.
But they're not as bad as you probably
that's
are.
not near as bad as
No, no cosines of logs or something, okay. All right, and then you have an initial value. The first 2 are not, those are going to have some arbitrary coefficients. Number 7 is an initial value, so you should be able to evaluate your arbitrary coefficient. Number 8 is, again, this time it's an implicit solution, which I think will mean you can't solve it for y is equal to some function of x. It's going to be a multiple thing, but it is an initial value problem. And then number 9 is Euler's method, step size 0.1 to approximate 1.2. So you only have 2 steps to go. So that one's not nearly as bad as the other, but hopefully you can get your calculators working right on those.
Yeah, I gotta figure that out.
Okay. All right. So hopefully it's not as bad as the last one. Okay.
The last one wasn't that bad, except for
A couple problems, right? Okay. So anyway, those are they. And so try to get the first test on in to me as soon as you can. And if so, by Wednesday would be great. That way I don't have to put down, something at midterm. But okay. Yeah. So that's fine. And then get working on this one. I don't think you'll find this one take you as long. Not nearly as long, but yeah. And we'll get going on chapter 4. But chapter 4 is so long that you're going to have plenty of time to work on chapter 2. This is chapter 2 test. All right, good deal. Any questions? And we probably did use the whole time this